Hello. In this video, I'm going to show how to solve this problem involving a thermodynamic cycle. So we're told that we have n moles of a monatomic ideal gas that starts at B0, V0, T0. So pressure, volume, and temperature initial. They are first isochorically heated to the hot temperature, TH. Then they are isothermally expanded back to the starting pressure, and finally, the gas is isobarically cooled back to T0. Okay, that was a lot of words. Let's draw a PV diagram of that process. So number one, PV diagram. So I always put P on the vertical axis, V volume on the horizontal axis. I'll start right here. The first is isochoric, aka constant volume. So I'm going to expand to constant volume vertically, like that. Let me try to make a better line there. Okay, we're told we go from T initial. So T isn't on this plot. Remember, constant T lines are something like this. So that is a constant T line. So we start at this cold temperature and we go to some hotter temperature up here. And then we go change at constant temperature. So that's I'm going to follow this 1 over V curve back to my original pressure. So we'll call this here P initial, this volume here V initial. So we follow, so this first dashed curve here is the constant pressure or constant temperature curve, T initial. We don't follow it or anything. It's just, I'm just drawing it there for reference. This is the constant temperature at T hot. And then finally, we do an isobaric, aka constant pressure process, back to our original state. Okay, so there's three processes there. Process 1, process 2, process 3. Okay, so now let's analyze this thermodynamic cycle. So the first thing I'm going to do is I'm going to find the temperature, pressure, and volume after each of the steps. So after the constant volume expansion, well, it's a constant volume expansion. So the first thing I can say is that it ends at V naught. What happens to the pressure? Well, by PV equals nRT, if the temperature goes from T0 to T hot, the pressure must increase by the same fraction. So P naught times T hot over T initial. So that's my final pressure. Oh, okay. So that'll do that. Let's do PV equals nRT for the rest of these steps before I go into finding the heat, work, and energy for each of the steps. Okay. So after the isothermal process, well, isothermal means constant temperature. So if I went to T hot, I will stay at T hot by definition. We have P initial. We're going back to the original pressure. So what will the volume be? We can look at our plot here. So now we're doing this point over here. Our volume will be bigger than our original volume. How much more by? Well, so if you imagine going from here to here, you're keeping T constant. We're decreasing P, but increasing volume. So volume has to increase by the same ratio that pressure decreases. So my volume is equal to V naught T hot over T naught. And finally, after the isobaric, so process, we come back to the original volume, and presumably then also the original pressure, because it's a PV equals NKT. If N and K are constant, then apparently PVT all must go back to the original. Okay, so that's all of my pressures, volumes, and temperatures for those 3 points. Now, let's talk about the heat that goes into the gas, the work that leaves the gas, and the change in energy of the gas for each of these steps. The first thing I'm going to do is the isochoric process does no work. It's the vertical line. There's it's constant volume. There's no PDV, so it can do no work. What is it? So now I have to find its either Q or delta U. I'm going to start with delta U. Delta U is directly related to temperature. You may recall that that the internal energy is equal to D over 2 NKBT. In our case, we have a monatomic ideal gas, so D equals 3. So if I want to change in U, well, I'm not going to change D, I'm not going to change N, and I'm not going to change K. So I'm going to be changing temperature, so I can just do this with the final temperature minus this with the original temperature. In other words, the change in U will be 3 halves because D over 2, N, K, and then I want to do my final temperature, T hot, minus my initial temperature, T naught. So that is a change in U. Okay. Once I have work and change in U, I can get Q fairly easily because the change in U, internal energy, is equal to how much you add, Q in, minus how much work goes out. Work goes out as 0 in this case, so delta U and Q are the same. So apparently Q is 3 halves NK T hot minus T naught. Okay, so first process is done. Let's move on to the isothermal process. If this is an isothermal process, the temperature is not changing. Internal energy is directly related to temperature, so if the temperature doesn't change, the internal energy doesn't change. So that's 0. Okay, let's see here. Work. So you may recall the formula for the work of an isothermal process. Work is equal to NKT ln of V final over V initial. So what temperature is this? This is the temperature. It's an isothermal process. This is the temperature of that process throughout its duration, which in this case is T hot. So the work will be NK T hot, the natural log of a ratio. Okay, so we want the final velocity, the final volume over the initial volume. So if I take this divided by this, because this is my final volume of the isothermal process, the initial volume of the isothermal process, take this divided by that, I just get T hot over T naught, or T initial. So in general, the work done by an isothermal process is as a ratio of the volumes. In my case, I'm going to have the ratio of the temperatures simply because the ratio of the volumes is directly proportional to the ratio of the temperatures. Okay, so that gives me work. I can then use the first law of thermodynamics. The delta U doesn't change, so all of the work I do must go into heat. So those must be the same. Q must equal W. So we can also write NK T hot natural log of T hot over T initial. Okay, sounds cool. And then I'm down to the isobaric process. So now I'm down to the last process coming back. I'm going to start with delta U again. I know my temperatures, so I can write the temperature, the internal energy change in terms of temperature again. This is 3/2 NK T final, which is T, our final temperature is back to the original temperature, T naught, minus our starting temperature, which in this case is the hot temperature, like so. You may notice that this is negative of this. So if you add all of the internal energies, the delta U for all three of the processes together, you get 0. This is necessary. It's a cycle. You come back to the original state. Delta U for an entire cycle must be 0. This is because if you come back to the original state, well, it's back in its original state, U has to be the same. This is not true of Q and W. Q and W only have to add up to 0 between them, or well, subtract up to 0 between them. But U has to come back to 0 because it is a what is called a state function. Okay, so it is kind of cool that that is back to 0. Now let's do our work and heat. So if I can either get one or the other. If I get one or the other, then I can use the first law of thermodynamics to find the second one. So which of these is going to be easier? Well, I'm going to do work because work is PDV. That's the area under the curve. This is a fairly straight area to calculate. You have a constant pressure. So the work is equal to P naught times final volume minus initial volume. So final volume is V naught. My initial volume is V naught T hot over T initial. You can write this as P naught V naught 1 minus T hot over T initial. But you may recall that PV is equal to NKT. So NKT naught 1 minus T hot over T initial. I can then multiply the T initial back in, NK T initial minus T hot. So any of these would be correct. Answer, we could use this is our answer. We could use this is our answer. I'm going to put in this last one. It seems the simplest to me. So N K T initial minus T hot. Okay. And for this one, I could just use the first law of thermodynamics here, conservation of energy, this value and this value to deduce that value, but I'm actually going to do it in a separate way. The way I'm going to do it is with CP. So you may remember that the constant pressure heat capacity, CP, is equal to D over 2 plus 1 NK, which means the heat needed is that times delta T. D in my case is 3, so 3 over 2 plus 1 is 5/2. So Q is equal to 5/2 NK delta T. So I can go put this in as 5/2 NK. It's supposed to be a K. A little better. And K delta T. So my final temperature is T initial. My initial temperature was T hot. So that's that. You can add these together, and you can see that this plus this indeed equals that. You do indeed get the first law of thermodynamics. So that fills out this table. And answers number 2. The last thing we're told to solve in this problem is to find the total work done. So 3. The total work done is equal to the area of this area inside the PV curve. Basically, we just need to add up all of the works. Okay, so there's only two works that are non-zero. That's the top work and the bottom work. This guy over here didn't do anything. So we get the first one. So work total or net is equal to n k T hot natural log of T hot over T initial minus nk T initial minus T hot. Plus. Okay, this is a positive because I'm just adding these two together. But you will notice that this number here happens to be negative, right? Because T hot is bigger than T initial. So this is negative. That's the bottom area here. This term here is positive. That's the full area under here. So if you subtract those, this minus this, but it's already negative, you would get the green area. So that is the net work, which, interestingly enough, will also be the net heat because the internal energy came back to where it is and where it started. Okay, and that's how you solve this thermodynamic process.